My name is Suneel Konidala. I'm a senior manager at Accenture. I'm part of the data and AI practice. I'm also a Databricks champion. I work at the Databricks COE with a focus on global enablement, like training, certifications for our global workforce. And I'm here with my good friend and colleague Murali to talk over about use case where we leverage, how we leverage Databricks to solve one of the real life challenges. And I'm going to hand over to Murali for a quick introduction, then we'll go over the agenda.
Sure. I am Murali Krishna Madireddi. I'm part of Accenture Modern Engineering team, part of data engineering, data and AI practice. I am also a certified Databricks solution architect. So that's my background. Thank you.
Thanks, Murali. So today what we are going to cover is we are going to cover a use case, and we'll review the architecture we deploy to solve this problem. And then we'll spend some time on the DLTs. DLTs we heavily use in the solution, why DLTs are important. And we move on to a topic which is dear to our mind here, the structured streaming. Again, this is something we use heavily, and in the process we learned some lessons, and we got to do some optimizations, customizations to overcome those challenges. Those will be covered in the intelligent streaming, and we'll make sure that we leave enough time in the end for any Q&A. Right? Before we go, a quick overview about Accenture. We are the #1 Databricks partner since 2019. We've been partner for a long time, but we are the partner. We've been winning the Partner of the Year award since 2019. If you have seen the news, even this year, we were the one. So we did not lose our leadership position in that space. Within the Databricks practice, we might have implemented over 100 Databricks solutions across multiple clients in all the clouds. We would say AWS, Azure, and Google platforms. We built more than 17 or so assets to speed up cloud migrations and accelerate those journeys. And it's not possible without a good number of trained resources. We are very happy to say that we have a 4,000 strong team of Databricks professionals across the globe helping our clients. And among these 4,000 people, we got more than 700 people certified in Databricks. And within that 700, we are close to 30 people who achieved the Databricks champion badge. Right? This is one of those highest accreditation or badge Databricks provides, and Accenture got more than 30 people. So moving on, when it comes to this use case, our goal is to develop a framework that can ingest, curate data coming from batch and real time, and will also managing all the dependencies between incoming data. This all we want to manage based on metadata at a cost-efficient way, right? The summary is which organization doesn't want to do. Every organization wants to solve the complex problem in a cost-efficient way, and we are fortunate enough that we worked one of them. I would say that the problem is very complex, but it's not so unique. Every organization today has variety of data sources. They come in batch, they come in real time, they come in various formats. You need to handle all of them, right? So in our case, similarly, we were getting data from on-prem, from multiple RDBMSs, you name it, like Oracle, DB2, data warehouses like Teradata, even hierarchical mainframe databases like IMS. And then the data comes, we were doing like a bulk extracts for one-time migration, and we're getting data in a CDC for all the change data coming from operational systems. And data has variety of file formats, right? CSV, JSON, XML, you can expect in any organization, right? And we need to manage both SCD1, SCD2 type of operations, and it's not common across the enterprise, not common across for all the tables, but certain tables we have to do SCD1, certain tables we have to do SCD2. And while we process this data, we need to manage the data quality, and we also need to do data curation, right? We anticipate that the schema is not going to be static, as well as we got to do the schema validation, as well as the schema changes, we want to make sure that the schema evolution is also handled, right? And in a typical Lakehouse architecture, as the data gets moved from zone to zone, we need to handle the transformation. So our solution are in our architecture, the data stores are not only the delta tables, we also have cloud RDBMSs like BigQuery, PostgreSQL. We need to ingest data for consumption purposes. In a nutshell, this looks like similar to many enterprises we see are having the same challenges. So in a way, it's a complex problem, but it's not so unique, right? We see this again and again. The architecture we built is, as I said, from on-prem, we are getting data from we have all kinds of data stores, DB2, Teradata, Oracle, IMS, and we were getting historical data. We were extracting through multiple utilities like export utilities or JDBC kind of solutions. Whereas for CDC, we were using replication tools like Informatica, and then all the bulk extracts, they go directly to the Google Cloud, and from there, our pipelines will process the data. Whereas for the CDC replication, we were fetching them through Kafka. We were getting the data through Kafka from on-prem, and once it goes to the raw zone or the landing zone, the data gets processed in the same way, and there's no difference between whether the data came from batch process or the streaming process. From landing, I'm sure everybody is familiar with this. We following the Medallion architecture, we were doing the data validations. All bad records we were quarantining and keeping them in the quarantine zone, whereas good records we move to raw zone, then they go to curation process, and they go to curated data. From curated, we were, again, sending data to both for operational and analytical needs. Operational data goes to Postgres, and analytical data goes to BigQuery, and which will be consumed by all the BI applications. Whereas our operational data is consumed by APIs. As you can see, most of our pipelines are built on Delta Live tables from landing to curated. And our solution also needs to include non-DLT tables also, right? For example, BigQuery and Postgres, they are non-DLT, but our pipeline needs to address ingesting data into non-DLT tables. So how we solve this problem, right? We built a framework. It's based on metadata. It supports batch streaming. It can load data into data lake as well as consumption layer like BigQuery and Postgres. It can perform, it should perform, and we build like such a way that it can do for every ingestion, we can do this audit, balance, and control checks on the data coming. And we were capturing a ton of data observability metrics in the process. Something innovative we did was, I'll go in detail about this later. We built a system or a process where it can automatically perform out-of-sync events, out-of-sync checks. If the data between source and target is not matching in terms of schema or counts, we built a process to validate that and request to rectify that automatically. Again, we'll go in detail about that later. And our solution automatically generates all the Delta Live tables, right? It's all, since Delta Live tables is a SQL base, our solution was automatically generating those pipelines. And as well as I said, we were generating the structured streaming code also as part of the pipeline. In a simple, as I said, it's a metadata-driven framework. You come here and you define all your source and target tables. We were taking care of all the pipelines, following the industry best practices of doing data quality checks, data curation checks, data, collecting all the data observability metrics. So that way we were gaining efficiency so that we don't expect all the developers to come and build pipeline for each use case. Okay. So how we did this, right? In a simple nutshell, we designed the system such a way that a data analyst or data engineer can come and create the ETL specs in a simple tabular format, right? It's a simple Excel sheet. You come and define your source tables and target tables and define those mappings and define your data quality checks, rules you need to be processed, define your curation rules to be processed, and if you have any aggregation logic needs to be implemented, all of them go into that tabular format in a simple, anyone without a lot of technical knowledge can build that Excel sheet. And we were ingesting that into a Databricks table. So the main purpose of, it's solved in two ways, right, the specs. Our framework reads the specs and it generates a pipeline. So think about that, hey, you have a group of 10 tables to process. So we define those 10 tables in the ETL spec, and when we run the framework, it can generate the pipelines for us, and that can be scheduled in the Databricks, right? And it can manage all the dependencies between those tables. So the other benefit we saw was, since we are capturing a lot of good amount of metadata in the ETL specs, our support engineers, for them, it's a very valid repository to go and check for data lineage and what are the curation rules, what are the data quality rules we have implemented. And the same information has been sent to enterprise data governance tool like Colibra also. Okay. So moving on, as I said, we heavily leverage Delta live tables because they're very simple to use, and they automatically comes with the capability to manage dependency between multiple tables and zones. So we don't have to, all you have to do is define, this is the source for the so-and-so table. When the previous table gets loaded, the data can automatically move to the next table. In a way, it becomes very easy for us to manage data between multiple zones, right? And it can perform data quality checks. And another great benefit is the tables in DLT are automatically managed. You don't have to perform an external operation like vacuum or optimize. These tables are automatically managed. And since we have data stores outside Delta tables also, so we were able to integrate DLT workflows in the jobs outside DLT also. Again, all of these things we were able to do within Databricks, not using any external tools. So, as I said, another good solution or process we implemented is, we know as part of your regular data pipelines, we do validate. Hey, if I'm getting 1,000 records in the incoming file, I'm processing those 1,000 records and validating those counts after every pipeline execution, right? But we do know that in any enterprise, over a period of time, the tables, the schema can drift. Some examples are, if the source system adds new tables, and if it is not defined in your replication tool, it is not going, sorry, if the source system added a new column, and if it is not defined in the replication tool, it is not going to pick that new column. If it doesn't pick, your target system in the cloud is going to miss that column, right? And it can happen for a few days, then later if you realize, then you have to go and fetch the data from source system and replicate, right? So we built a system where we periodically, in the beginning we were doing like twice a day. Periodically we get schema from source, we get schema from target, we are comparing for all kinds of attributes, names, data types, precisions, and all those things. And if there is any mismatch, we will automatically triggering a process to go fetch latest schema from the source system and update the target system. Right? And we are also alerting operations team saying that there is a schema mismatch so that they can go take corrective actions on their end. Similarly, for counts, we were doing the same thing. We know that it's not going to be 100% match between source and target, right? There could be, since these are very dynamic operations, right? There could be a time period. We know that target system will be some difference in the count. So we define thresholds. If the counts are beyond the threshold, then again we define another event. And based on the event, we can automatically request a data extract dump from the source system and process the data to bring the counts to the mismatch to minimum level. Again, this looks like a very simple process here, but in the implementation it is not so simple because of the 24/7 operation, and you got to make sure that you are not taking outage. There are a lot of things went into picture or went into the design process to build this, but the interest of time, I did not go into detail about all the things we have implemented here. So I think with that, I'm going to hand over to Murali to talk about the next interesting topic, streaming.
Yeah. Thanks, Suneel. So why streaming? So the primary use case what we have is we want to fulfill all our data requirements using cloud. So the users, typical users are going to log into the portal, they want to update their address, they want to see the up-to-date information. Today that requirement is fulfilled using an on-prem database, right? When we ingest data into cloud, the expectations remain the same, right? They want to see the latest and greatest data, even in cloud as well, right? And even for business, it's a value add if we can quickly realize the cloud benefit by offloading the traffic on on-prem databases into cloud. So, oh my God. Yeah, I need to switch it. Sorry about that.
Need some help.
Okay. All right. So standard structured streaming. So let's assume that we have hundreds and thousands of tables on-prem. Likewise, in cloud, we have equivalent number of tables. So we have a job per table because every table in its schema is different. But high level, the requirement is to bring in data as quickly as possible so that the data freshness is maintained, right? So let's assume there are 100 tables, we need 100 jobs, right? So that's at a high level. So this model is good, but it is going to be expensive, right? When we have many tables to be ingested at a real time, it's going to incur high costs. In our case, right, it's not a continuous flow of data. We don't know when the data comes, when the updates can happen on on-prem database, but at the same time, like a batch workflow won't work for us, right? We can't schedule it for an hourly batch or 4-hour batch, right? It has to be as soon as the data comes, we want to process it, but we don't expect the data to come all the time, right? So this is an interesting situation in comparison to like a sensor data, right? Sensor data is always coming, no matter what, right? But we have during active window, we get more data. Annual enrollment, we have more data, but we may not get a lot of data during, let's say, during night, right? So that's a scenario what we have. So this is straightforward implementation. We have per database, we have multiple tables within it. Each database has got an equivalent Kafka topic, right? So we have a job that is reading Kafka topic and writing the corresponding Cloud SQL Postgres database. It reads the data, it converts the data types, performs SCD1 change detection, and merges the data into the final target. So kind of column rename, column typecast, data type typecasting, and also ingestion into Postgres. That's a standard structured streaming implementation. Then we thought about how do we make this model more efficient, right? So we don't want to spend this much cost on the clusters because there is a limitation on how many jobs can be there in a cluster, right? So how can we meet the same SLA and maintain the data freshness, but at the same time, how do we avoid a cost, streaming cost, right? So then we came up with this model. We have the same database level topic. In a topic, we have number of tables. We read the topic. Using thread pool as a concept, right? We create as many number of threads as we see it in the data. Let's say if I read a topic 1, I see 3 tables data. The number of tables are identified by the key within the topic. So I create 3 threads to write it to Postgres. Same thing if I see only 2 tables that have data, I create only 2 threads. So it's a iterative process. Read, create as many number of threads that are needed, and each thread is responsible for column type, data type conversion, rename, and SCD1 operation. Okay, and it goes back to reading. So the micro batch is like a read, create threads, write, and do the same thing again and again. Okay. So in this way, compared to the prior slide, we have, regardless of data, whether we have the equivalent number of threads, and in this case, we have the active threads equivalent to active data that is flowing in. Okay, and we meet the same SLO requirements and using this model, but because we have much fewer active threads, we need less number of cluster resources. So this is another view. We have structured streaming, the number of jobs and threads are set, whereas in intelligent stream, it all depends upon the data, right? Data arrival is a way to trigger an event for us to write data to Postgres, whereas structured streaming, there is no event in it, right? So that's a comparison. And so it's an iterative process. First iteration, we had 3 tables. Next iteration, we have 1 table, and so on and so forth. Okay, and the third one is the last one having 2 tables. So another advantage is there can be stalled streams, right? With a structured streaming, what we have faced is, let's say there are active threads, and if one thread is taking a lot of resources, the resources are not released back to the cluster promptly. In case of intelligent stream, each thread is short-lived, so get activated. Once it is complete, it is pretty much shut down. So going to the next slide, performance test. Suneel, you want to cover the details, performance test?
Yeah, sure.
Okay, yeah. So high level, we have like a 10 to 15 time reduction in number of clusters that are needed. That's what we found, but yeah.
Yeah. So a quick disclaimer about the performance test. We have certain goals, so we did the performance test just to make sure that our solution works for our capacity needs or not. We did not do a full-blown performance test to see how much we can scale with this solution. Given that what we did was we simulated a workload with some tables with the low transaction activity, some tables with medium, some tables with high, all of them coming and hitting our Kafka queues, anywhere from 100 transactions to 10,000 transactions per second. And we used a configuration cluster of with N2 HIMEM 16 with a driver equal to 1 and workers anywhere from 4 to 10. We picked 4 so that we don't want it to be start low and go scaling. We know that for the given workload, we might need at least few nodes to be up. So we started with 4, and it worked well. And once the test is done, we rolled up all the transactions to the minute level to see how much we were able to process, right? Given this cluster capacity, we were able to process anywhere from 30K to 100K transactions. And depending on, again, it depends on how many were available at that time in the incoming Kafka topics. If there is no data, we would process less. If there is data, we could process up to 100K. And on average, within a minute interval, we were able to process 40 tables. Again, this is for our particular use case. What we found was this is good enough for us to scale. Even if we get more data, more topics, we could scale up the cluster resources to consume. And compared to the previous structured streaming, the intelligent streaming, we were able to reduce the cluster resources and in another way, reduce the overall cost of the solution. Right? That's a key. And the simple concept is we were able to reuse the threads based on the active workload coming. If there is no data coming, we don't have to spend cluster resources. Right? So that's about intelligent streaming. A quick recap. As I said, we built a single framework to address various types of data loads in a cost-efficient way. And we leverage many of the out-of-the-box capabilities like DLTs, Apache structured streaming. In a short span of few weeks, we were able to onboard thousands of tables into our data lake platform. As I indicated, Accenture is the largest SI partner for Databricks. We have been the leading partner for the last 6-7 years. We are, as a team, we are very impressed with the innovation happening at the Databricks, the speed at which they're releasing new products or new features and positioning themselves as the leader in the data analytics space in the cloud. And I'm looking forward for great features like marketplace, delta sharing, and LLMs becoming mainstream this year. I'm sure I could have added a few more after this keynote speaker, but these slides are already frozen and sent to Databricks. But I'm sure you all had a good conference in the last few days. Me and Murali will be here for some more time if anyone have any questions. Sure, Tom.
Yes.